In this final lecture of Module 4, we want to spend some time discussing an important principle called LeChâtelier's principle. In the previous lecture, when we demonstrated using ice tables to do equilibrium calculations, I had mentioned that getting comfortable with those types of calculations will be very important going forward for dealing with and understanding future modules, specifically acid-base chemistry and solubilities. In this lecture, we really don't do any calculations, but the principles discussed in this lecture are as important as the calculations were in the previous chapter in understanding acid-base chemistry and solubilities moving forward. Now, if a reaction has reached equilibrium, one might ask the question, what would happen if a sudden change, like a change in concentration, pressure, or temperature, was imposed on this equilibrium? In other words, how does an equilibrium respond to a disturbance? Well, we describe the general response of an equilibrium to a disturbance by invoking LeChâtelier's principle. And LeChâtelier's principle is restated here in not the exact words of Le Chatelier, but I thought this was a good description. If a system at equilibrium is disturbed, it will shift to the right towards products or to the left toward reactants, whichever is necessary to at least partially counteract the disturbance. A new equilibrium will then be established. Well, let's give a little more detail about some examples of disturbances a system at equilibrium might encounter. One would be a sudden change in concentration, and that could be imposed by either adding or removing a reactant or product. If you add a reactant or product, the equilibrium is going to respond by shifting in a direction that uses up some of the added substance. That's consistent with Le Chatelier's principle, in which the equilibrium is shifting in a direction to partially counteract the disturbance. So if you add a reactant or product, the equilibrium will shift in a direction that uses up whatever you added. If you remove a reactant or product, the equilibrium will shift in the direction that produces more of the substance that is being removed. Another way you could disturb an equilibrium is with a change in pressure. This specifically covers reactions involving gases. If you reduce the volume of a gaseous reaction, it's going to increase the pressure, and it's going to cause the equilibrium to shift in the direction that produces fewer molecules. If there's fewer molecules, the pressure will drop. So if you increase the pressure by reducing the volume, the equilibrium says, okay, I'm going to respond to that by shifting in the direction, either left or right, that produces fewer molecules, because that will counteract what you're trying to do by squeezing or shrinking the volume. If you expand the volume of a gaseous reaction, it's going to cause a decrease in pressure. And again, the equilibrium is going to shift in the direction then that produces more molecules to try to counteract this, because producing more molecules would increase the pressure to counteract what you're trying to do by decreasing the pressure. If you have a gaseous equilibrium with the same number of gas molecules on both sides of the balanced equation, they would not be affected by changes in pressure. And finally, you could change the temperature, and A simple way of describing what happens is that an increase in temperature will shift the equilibrium in the endothermic or heat absorbing direction. If you decrease the temperature, the equilibrium will shift in the exothermic or heat releasing direction. And this is a time to remind you that changing the temperature also changes the value of the equilibrium constant, so we have to keep that in mind. Now, to illustrate each of these possible disturbances that we described on the previous slide, we can use as an example, the production of ammonia from nitrogen and hydrogen. So nitrogen plus 3 molecules of hydrogen can reach an equilibrium with 2 molecules of ammonia. The Kc for this reaction is well studied and well known. It's 0.058 at 500 degrees C. And you should note that this Kc value is rather small, which means that this equilibrium does not naturally favor production of ammonia, because remember, if the equilibrium constant is small, that means the equilibrium is reactant favored. So when this reaches equilibrium, there's not going to be a great deal of ammonia. We're going to have to deal with that later. We also want to remind ourselves that there is heat released going from left to right in this reaction. So when you do produce some ammonia, the delta H is minus 92.4 kilojoules per mole. It's an exothermic reaction going from left to right. Now this reaction is carried out on an industrial scale using what's called the Haber process. And this is a now well-established procedure using specific reaction conditions and catalyst in an attempt to get the highest possible yield of ammonia in the shortest possible time from a reaction that does not naturally favor the product side. Again, Kc is small. We want to make ammonia. It doesn't naturally favor production of ammonia. So we're going to have to try to disturb this equilibrium in some way to maximize our yield of ammonia. Turns out that ammonia is a very, very important product. A large percentage of ammonia goes toward agricultural uses, the production of fertilizers, which includes the direct spraying of anhydrous ammonia on farmers' fields. You've probably seen that in Illinois. So let's illustrate how the equilibrium involved in the production of ammonia will respond to various disturbances. So what we're going to try to do is see if we can take advantage of how this equilibrium responds to external disturbances to maximize the yield of ammonia. So let's start with a change in concentration, or suddenly changing the concentration of reactants or products, and see its effect on this equilibrium. Let's suppose that we had a 2-liter container and it contained 0.922 molar nitrogen, 0.767 molar hydrogen, and 0.155 molar ammonia. And we're going to ask, is this system, as written with these concentrations, at equilibrium? Well, of course, we want to calculate a reaction quotient and compare it to Kc. So if we calculate a reaction quotient using the normal rules for calculating these, you see that the numerator is squared because of the 2 in front of ammonia. And the 0.767 is cubed because of the 3 in front of the hydrogen. We get a Qc value of 0.058. And since the Qc equals the Kc, we say, well, the system's now at equilibrium. These conditions are actually equilibrium conditions. So now let's disturb this equilibrium. Let's suppose that we directly inject that container with 1 mole of hydrogen gas. And that would cause, and I don't show you the calculation to prove this here, but that would cause the concentration of hydrogen to suddenly jump to 1.267 molar. So remember, it's at equilibrium here when the concentration of hydrogen is 0.767, and we're going to add an extra mole of hydrogen to bring the total concentration of hydrogen up to 1.267. That would be what we added plus what was already there. Now, according to LeChâtelier's principle, the system, meaning this equilibrium, will respond in a way to counteract what we've just done, adding hydrogen. Now, to counteract that, it's going to try to use up the hydrogen we added. So it should shift to the right towards products and form more ammonia to use up at least some of the added hydrogen. And that's going to happen as long as we have enough nitrogen in that container to react with as much hydrogen as the system wants to react in order to respond to our disturbance. Now, we would arrive at the same conclusion by calculating a new QC value. And what I mean by the new QC value is that right after the addition of this hydrogen, all of the concentrations in this container are the same except the hydrogen. Instead of it being 0.767, it's 1.267. Under those conditions, QC is 0.0128. And as you can see, the QC is now less than the KC, so the system shifts to the right to reach equilibrium. Now we might ask, what would be the concentrations of reactants and products when equilibrium is reestablished after this disturbance? Because remember, LeChâtelier's principle said the system will respond, it'll shift left or right in a way to counteract what we're trying to do to it, counteract the disturbance, but then a new equilibrium will be reestablished. So let's see if we can figure out what the situation looks like when equilibrium's been reestablished. So basically we're asking what would be the concentrations of reactants and products when equilibrium is reestablished after this disturbance, the sudden addition of hydrogen. So what I'm going to do is I'll set up an ice table, and for the initial conditions, we're going to put in the concentrations immediately after the injection of additional hydrogen, but before any movement to reestablish equilibrium. So we kind of freeze things in time, and we say right after the injection of hydrogen, the concentration of nitrogen is still 0.922, hydrogen went up to 1.267, ammonia still at 0.155, so we freeze it in time at that point and say that's our starting point. Now remember, the 1.267, of course, includes the added hydrogen. The change row, of course, would be minus x, minus 3x, and plus 2x, the coefficients from the coefficients in the balanced equation. But also we established previously that the reaction will shift to the right to reach equilibrium. So these would be the right signs for x. And now we just fill in the table as we would for problems that we saw on the previous lecture. I think I mentioned at the beginning of this lecture that there wouldn't be any calculations. Well, I guess I lied. There is one calculation, but it's very much like what we did in the previous lecture. But it does prove a point here. Let's go ahead and do this calculation of finding x. So we put in the equilibrium concentration expressions for ammonia and for nitrogen and for hydrogen. Remember to square the ammonia concentration and cube the hydrogen concentration, and you set this whole expression equal to the Kc. Now, it turns out that this is much more complicated than a regular quadratic. So I went to wolframalpha.com to solve this, and I get an x value, or the algorithm in wolframalpha.com gave me an x value of 0.0533. So let's calculate the concentrations at this new equilibrium. The concentration of nitrogen would be 0.922 minus X, or 0.922 minus 0.0533, or 0.869. The concentration of hydrogen at the new equilibrium would be 1.267 minus 3X, which turns out to be 1.107. And the concentration of ammonia was 0.155 plus 2X, so that would give us 0.262 molar. If we plug these concentrations at the new reestablished equilibrium, we do get the correct Kc value of 0.058. So this checks out. So let's summarize what's happened. Here's our equilibrium, and we have the equilibrium concentrations before addition of hydrogen. Remember, this system was happily at equilibrium before we disturbed it. And then we calculated the equilibrium concentrations after the addition of hydrogen. So here's the concentrations of reactants and products when it was at equilibrium before we disturbed it. Here are the concentrations of reactants and products at the new equilibrium after we disturbed it and the system responded to the disturbance. And you can see that both sets of equilibrium concentrations check out. So here are some things to note about this. Addition of a reactant, in this case hydrogen, did cause the system to respond by shifting in the direction to use up the added hydrogen. In other words, LeChâtelier's principle was followed. Note that the nitrogen concentration is lower and the ammonia concentration is higher after the hydrogen is added and the system reestablishes equilibrium. So remember, we added extra hydrogen and the system responded by using up some of that hydrogen, but it also had to use some nitrogen and produce some ammonia when we did that. Now, did the system respond and use up all of the added hydrogen? No. Remember, the hydrogen concentration suddenly jumped to 1.267 or something like that, 1.2 something. And when the system responded and reestablished equilibrium, it brought the hydrogen concentration back down from 1.2 something to 1.107. So no, it didn't add or use up all of the added hydrogen, but the system did respond and use some of it up and reestablished a new equilibrium. Are the concentrations of nitrogen, hydrogen, and ammonia after equilibrium is reestablished the same as before addition of hydrogen? And we've already pointed this out. No, but LeChâtelier's principle only requires that equilibrium be reestablished, not that it be reestablished with the original set of equilibrium concentrations. So what are other ways we could cause this reaction to be pushed to the right? In other words, if we want to maximize ammonia concentration, what other things could we do in the realm of changing concentrations? Well, we could also add additional nitrogen. That would cause the system to shift to the right towards ammonia production. Or we could remove ammonia as it forms. So if we did that, it would cause the reaction or the equilibrium to shift to the right, because if you're removing ammonia as it forms, it will respond to that disturbance by trying to form more ammonia. So either or both of these disturbances would encourage the equilibrium to shift to the right towards production of ammonia. So LeChâtelier's principle can be used to maximize the yield of ammonia in the Haber process. So during this industrial process, continually adding reactants while simultaneously removing ammonia basically pulls the equilibrium to the right. I guess it would be more correct to say that adding nitrogen and hydrogen pushes to the right, and removing ammonia as it's formed, pulls to the right. In any event, it's a way to maximize the yield of ammonia. In general, if you continually disturb a reaction, in this case by continually adding reactants and continually removing the product, what you're doing is you're forcing the reaction to continually seek or chase after equilibrium. The trick is to create conditions where the reaction is doing the chasing in the direction you desire. Now let's move on to some other ways to disturb an equilibrium. The second on our initial list was a change in pressure, and remember this was for reactions involving gases. And as mentioned previously, we could change the pressure by suddenly increasing or decreasing the volume of the vessel containing the reaction. So we can look at an example using the Haber process. When you look at this equilibrium, you want to notice that the balanced equation shows 4 molecules of gas on the reactant side. There's 1 nitrogen and 3 hydrogens, while there appears to be only 2 molecules of gas on the product side. So there are unequal numbers of moles of gas on each side of that equilibrium symbol. Now, an equilibrium that has an unequal number of gas molecules on each side will be affected by a sudden change in pressure caused by a sudden change in volume of the reaction container. If you increase the total pressure by making the container smaller, in other words, you squeeze the equilibrium as far as its volume, the equilibrium will shift in the direction of making fewer molecules until a new equilibrium position is attained. If you squeeze the volume that this equilibrium exists in, it's going to respond by trying to counteract the disturbance you're causing. If it shifts toward making fewer molecules, the pressure will drop, because remember, pressure is directly proportional to the number of gas molecules present in that volume. If, on the other hand, you decrease the total pressure by making the container larger, the equilibrium will shift in the direction of making more molecules until a new equilibrium is reestablished. So for the Haber process, high pressures would maximize the yield of ammonia because the equilibrium would shift towards products, which for this reaction is the side with fewer molecules. We will try to illustrate this with a couple of pictures on the next slide. So we have 2 cases here. Case 1, where the volume is suddenly decreased, and then we'll look at the second case where the volume is suddenly increased. So going back to the volume suddenly decreasing, let's suppose the original volume containing the reaction at equilibrium is illustrated by the size of this box. Here's the equilibrium in this container. And now we're going to shrink the volume of the container, and we have a smaller volume. If we do that in a sudden way, the pressure is suddenly going to go up. Well, the system is going to respond by shifting in the direction that produces fewer molecules. So it will cause the reaction to shift towards products. That's the side that produces fewer molecules in order to counteract the suddenly higher pressure that we imposed on it. In case 2, let's look at the possibility of suddenly increasing the volume. So we start with our original container containing our equilibrium, and let's suppose we suddenly increase the volume, which I've tried to illustrate here by making the box bigger. That's going to cause a sudden drop in pressure. And so the equilibrium says, by LeChâtelier's principle, I'll shift in the direction that counteracts what you just did. So I'm going to shift in the direction that produces more molecules. In other words, it's going to shift back toward reactants and then reestablish a new equilibrium. Let's move on to looking at a change in temperature for a disturbance. Now, again, I'm going to remind you that changing the temperature actually changes the value of the equilibrium constant K. However, this in no way nullifies the analysis on this slide, and in fact, our analysis is going to be consistent with this change in K. Restating what we stated on the first slide, an increase in temperature, which would be a disturbance, shifts the equilibrium in the endothermic or heat-absorbing direction. In other words, if we add heat by increasing the temperature, the system responds to use up that heat, and it would do that by shifting in the endothermic or heat-absorbing direction. If you decrease the temperature, the equilibrium will respond by shifting in the heat-releasing or exothermic direction. Now, one way you can illustrate this is by simply thinking of heat as a reactant for an endothermic reaction or a product for an exothermic reaction. Let's go back and look at our Haber process, the production of ammonia. We remind ourselves that the Kc is small, but more importantly, we remind ourselves that this is an exothermic reaction as written. And when we say that, we mean going from left to right, that heat is released. It's an exothermic reaction. Delta H is negative. So this, of course, means that if you run the reaction in reverse, so the reaction goes backwards, and I've written here ammonia going back toward reactants. If you wrote the equilibrium that way, then going from left to right would be endothermic, or it would be heat absorbing. Now in an exothermic reaction, which is what this is, written like this, with N2 and H2 on the left going toward ammonia, we could add heat as a product. So we have our equilibrium and we concede the fact that heat is given off, so we're writing it as a product on the other side of on the right side of the equilibrium symbol. Now disturbing this equilibrium by increasing the temperature, in other words by adding heat, would cause the equilibrium to shift in the direction that uses up the heat, to the left toward reactants. Thus, an increase in temperature shifts the equilibrium in the endothermic or heat-absorbing direction. Now, disturbing the equilibrium by decreasing the temperature, that is by removing heat, would cause the equilibrium to shift in the direction that produces heat, left to right toward products. Thus, a decrease in temperature shifts the equilibrium in the exothermic or heat-releasing direction. So for the Haber process, it appears that keeping the temperature lower would favor the production of ammonia. Because again, if we lower the temperature, the system will respond by producing ammonia and heat, and the heat production is to counteract our lowering the temperature. Now from the previous slide, we recall that an increase in temperature shifts the equilibrium in the endothermic direction. A decrease in temperature shifts the equilibrium in the exothermic direction. Now in this slide, we'll examine how the value of K changes with temperature. And by examining, I mean I'll just show you some data. This is actual experimental data. So if this reaction is carried out and allowed to come to equilibrium at these various temperatures, the equilibrium constant is determined at each one of these temperatures, and you'll notice that as the temperature increases, the value of the equilibrium constant decreases. We can see if this experimental data is consistent with the value of Kc we've been showing you. The value was 0.058 at 500 degrees C, which is 773 K. And you can see between 700 and 800 would be 773 K, and 0.058 is between 0.3 and 0.04. So this value we've been quoting here is consistent with this data. So we want to note here that the K value decreases as the temperature goes up. This means that increasing the temperature, in other words, adding heat, results in less product when equilibrium is reached. That is, increasing the temperature favors the left side, the reactant side, something we already concluded on the previous slide. So it appears that keeping the temperature lower would favor the production of ammonia. But we might have a little problem here because, as you recall, lower temperature means a slower reaction, if you recall from the kinetics module. So maybe we need to use a catalyst here.
Recall from the kinetics module, the previous module, that addition of a catalyst provides an alternate pathway for reactants going to products, and that this alternate pathway has a lower activation energy. However, it does not affect the position of the final equilibrium. In other words, addition of a catalyst just speeds up how fast you reach equilibrium, but it doesn't really affect the position of that equilibrium. In other words, it doesn't affect the equilibrium constant. Let's look at our reaction of nitrogen and hydrogen to form ammonia. We can draw an energy level diagram for this, and you've seen these before. We have the reactants, nitrogen and hydrogen, at a certain energy level. We'll just make it arbitrarily here. The important thing here is that it's an exothermic reaction, so the products are at a lower energy than the reactants, and the enthalpy change here is minus 92.4 kilojoules per mole. What I've marked here is the activation energy for the forward reaction when no catalyst is present. So nitrogen and hydrogen have to get over this activation barrier to make ammonia. If we looked at the reverse reaction, again, not in the presence of a catalyst, the reverse reaction would have this activation energy to go backwards to reactants. If we add a catalyst, we provide this alternate pathway. This alternate pathway has a lower activation energy for the forward reaction, so I've marked this the catalyzed pathway. That means that the reverse reaction in the catalyzed pathway would be marked right here. And what you can see is that both the forward and reverse activation energies for the catalyzed reaction are lower than the activation energy of the forward and reverse reactions in the uncatalyzed reaction. Ultimately, what this means is that the reaction will reach equilibrium faster when there's a catalyst present. However, the actual position of the equilibrium is no different between the uncatalyzed and the catalyzed pathway. In fact, the position of the equilibrium, ultimately the equilibrium constant, actually is related to what's called the free energy change for the reaction. And the free energy change is at least partially calculated from this enthalpy change. We'll talk more about that in a later module. Again, Note that the addition of a catalyst lowers the activation energy for both the forward and the reverse reactions, which means the reaction reaches equilibrium faster, but the position of that equilibrium, which again we said is related to this energy drop from reactants to products, is unchanged. Let's now try to summarize all the conditions necessary to maximize the yield of ammonia in the Haber process. Well, what are the conditions we want to run this reaction under? We said we want to continuously add nitrogen and hydrogen. This pushes the equilibrium to the right toward making ammonia. We want to continuously remove ammonia as it's formed. This pulls the equilibrium to the right. Running the reaction at high pressure is a good idea because the high pressure favors the side of the equilibrium with fewer molecules, which in this case is the right side toward ammonia. Running the reaction at lower temperature favors the exothermic direction. Well, remember the exothermic direction is to the right, and so we want to run the reaction at lower temperature. And to offset the kinetic effect of running it at lower temperature, we'll add a catalyst, which we said increases the rate at which the system attempts to reach equilibrium. Just to reemphasize, running the reaction at lower temperature has the consequence of slowing down the rate at which the system reaches equilibrium. We can add a catalyst, that helps, but ultimately we have to reach some compromise here in the conditions between temperature, addition or subtraction of reactants and products, and so forth. Well, what are the compromises? For the Haber process, this compromise turns out to be running the reaction at around 400 degrees C and at fairly high pressure in the presence of various types of catalysts. Nitrogen and hydrogen are injected continuously in a 1:3 ratio, and then at some point the reaction or equilibrium is cooled, which makes the ammonia condense out as a liquid. The unreacted nitrogen and hydrogen, which do not condense out as a liquid, are then recycled back into the reaction stream.